This lesson is on Unit 1.3, Elemental Composition of Pure Substances. So the law of definite proportions just tells us that a given compound always contains the same proportion of elements by mass. So if I were to look at a compound, for example, like water, it will always have a mass ratio of 2 to 1 in terms of hydrogen and oxygen. Same thing with if I were to change that, like where I have H2O2, it's no longer water, so it's going to have a completely different properties of that particular compound. So if I wanted to find the percent composition by mass, the percent by mass is equal to mass of the element in the compound that we're particularly looking to see what percentage of mass percent it has, divided by the mass of the total compound. So we find the molar mass of the compound and then times 100 since it is a percentage. Okay, a lot of times whenever we talk about percentages, I will say part divided by whole. Okay, this is just an easy way to remember with any percentages whenever you're finding them, whether it's in chemistry or not. You can always kind of fall back on that part divided by whole. So in the case of mass composition, we want to know what part that particular element makes up the whole compound. So for this first example, it wants us to find the percent mass of iron. So iron is the part, and then our whole is our iron 3 oxide. So first we need to determine the formula for iron 3 oxide. Iron is a transition metal, so in order to determine its oxidation number, it gave it to us there in parentheses. So the Roman numeral 3 lets us know that iron has an oxidation of +3. And then oxide is just oxygen, and looking at the periodic table, it has a oxidation number of 2. So when I crisscross, my formula will be Fe2O3. Okay, so now that I know that, I know how much iron is in this compound, along with I can determine the molar mass of the total compound in order to plug it into the formula. So my mass of iron in the compound, I do have 2 moles of iron in the total compound. So in order to find the mass of iron in this compound, I'm going to do 2 times the mass of iron off the periodic table. So my mass iron would be 111.7. For my actual molar mass of the compound, I'm going to take 2 times the mass of iron plus 3 times the mass of oxygen. So the total mass of the compound is 159.7. Okay, so in order to determine percent mass, I'm going to just do part divided by whole. So the mass of just the iron, which is 111.7, divided by mass of the whole, and then times 100 because it is a percentage. And I got that 70% of the compound mass comes from the iron. Okay, for the next one, what mass of carbon can be captured from 10 grams of ethanol? So for this one, I can set up a ladder system to kind of get through it, but then we'll kind of look at what percentage that is from the original amount. So for this, I'm starting with 10 grams of ethanol. And since I'm in grams, I want to go to moles of ethanol, and then from there I can determine from 1 mole of the ethanol how many moles of carbon. Looking at in the formula, there is a 2 here, so there are 2 moles of carbon for every 1 mole of ethanol. And then from there, I can convert 1 mole of carbon into the mass of carbon. So I have my grams of C2H6O has to drop down since it was up above. And I'm going to moles of C2H6O Okay, my mass would just be the molar mass, so I would add, or I would take 2 times the mass of carbon plus 6 times the mass of hydrogen plus the mass of oxygen to get a molar mass of 46.068. So now I'm in moles of ethanol. So in 1 mole of ethanol, for carbon, there are 2 moles of carbon based off of the formula. So now that I'm in moles of carbon, I can now go to grams of carbon. I have grams and moles, so anytime we have grams to moles or moles to gram, we're going to use the molar mass. So the molar mass of carbon off the periodic table is 12.01. So when I multiply across, and divide, I get 5 grams. So looking back at the original problem, if 5 grams is how much of the carbon we can get from the 10-gram sample, carbon must make up 50% of the overall mass of the compound. So when we're looking at the formulas, we actually have 2 separate formulas that we can distinguish about different compounds. We have the empirical formula, which is the lowest ratio of the elements in a molecule. Okay, and we'll kind of give an example of this, but it is that lowest ratio, like a 1-to-2 ratio or a 1-to-2-to-1 ratio, depending on how many different elements make up that compound. The molecular formula lets us know the actual number of each element in a molecule. Okay, so for example, I might have a molecular formula of C6H6. Okay, so it's telling me I have 6 carbons connected to 6 hydrogens. But its empirical formula would be the lowest ratio between the 2. So they are both divisible by 6. So its empirical formula is actually a 1-to-1 ratio. So just CH. Okay, so the relationship between molecular formula and empirical formula, basically we just multiply the empirical formula by some type of multiplier. So we're going to kind of go through the steps on how to first find empirical formula and then from there determine molecular formula based on the given molar mass of the compound. Okay, so this phrase here I'm going to say quite often, and it's one that you should memorize. It just helps you kind of walk through the steps. It kind of flows very easy for you to kind of memorize to just help you know what step you need to move on to in order to determine the empirical formula. So its first is percent to mass, mass to mole, divide by small, multiply to whole. So percent to mass just means that generally they're going to give you the problem in percentages. But if they don't, sometimes they give them to you already in grams. Then you don't have to worry about this step. It's already in mass. But percent to mass, all we do is we change the percentage sign into grams. The next step, mass to mole, we're going to use the molar mass of that element in order to convert the grams into moles. We're then going to divide by small. We'll kind of talk more about that once we actually have some numbers. And then multiply till whole. We just need to have whole numbers in order to determine our empirical formula at the end. So let's start with this first example. It says white pigment paint is a compound of titanium and oxygen. So we have 2 elements that make up this compound. It says that it contains 59.9% titanium by mass. Determine the empirical formula. So they only told us the percentage by mass of titanium and not of the oxygen, but because there's only 2, we know that they have to add up to 100%, so we can easily determine what the percentage of oxygen is. So step number 1, percent to mass. I'm going to take my 59.9% percent and change it to grams of titanium and put it over 1 because we're going to set up some ratios to get them into moles. And then for oxygen, if I subtract 100 minus my 59.9, I'm going to get 40.1 and then grams instead of percent of oxygen over 1. Okay, so we did the first step, percent to mass. The next is mass to moles. So since I'm starting with grams of titanium, that needs to drop to the bottom so that they cancel. I'm going to moles of titanium using the molar mass of titanium off the periodic table. The mass is 47.87. And then same thing for oxygen. I started with grams of oxygen, so it needs to drop to the bottom. We're going to moles of oxygen. We're going to use the molar mass off the periodic table, which is 16. So if I solve for this, I will have converted mass to moles. So for titanium, I get 1.25 moles. For oxygen, I get 2.51. Okay, the next step is divide by small. So if we look at these two numbers, I have 1.25 and I have 2.51. Of these two numbers, 1.25 is the smaller number, so I'm going to divide each of the numbers by the smaller number. So 1.25, 1.25, and I'm going to get 1 and 2. Okay, so we divided by small, multiplied till whole. Notice these are both whole numbers, so we don't have to worry about that last step of multiplying till whole. If you have like a 1.5 for one of your answers, we would have to multiply each of the numbers by 2 in order to get whole numbers for both of them. So these numbers represent the subscripts that we're going to apply to each of the elements to come up with the empirical formula. So the empirical formula for this problem, titanium, I would have 1 mole. Oxygen, I would have 2. So that is to find the empirical formula. To find the molecular formula, the mass must be given as the molar mass. So they'll tell you the molar mass of the compound is whatever it is. Okay, and once we have the molar mass of that, we're going to take the molar mass that's given. It's generally a large number. And we're going to divide it by the empirical mass, which is a smaller number. So then it'll give us a whole number that that's gonna be like our multiplier that we're gonna multiply each of the subscripts by. So for this practice problem, a sample of a compound of nitrogen and oxygen contains 1.52 grams of nitrogen and 3.47 grams of oxygen. Notice they didn't give us percentages, so we can kind of skip that first step of percent to mass. It's already in mass, so I'm gonna go ahead and write those down. So I have 1.52 grams of nitrogen over 1. And then 3.47 grams of oxygen over 1. It tells us that the molar mass of the known compound is 92 grams per mole. So that would be that molar mass, that larger number that's going on top. We just have to find the empirical formula so we can find the empirical mass in order to divide to figure out how much we need to scale up our empirical formula by. So we already did the percent to mass because there was no percentages. So we just already have the mass. The next step is mass to mole. So grams of nitrogen are going to drop down. We're going to moles of nitrogen using the molar mass of nitrogen off the periodic table. And then same thing with oxygen. There's 16 grams of oxygen and 1 mole of oxygen. So I'm going to get 0.108 moles of nitrogen and 0.217 moles of oxygen. Okay, so we did percent to mass, mass to mole. Now we're going to divide by small. So if you look, this is the smaller of our two numbers. We're going to divide each of them by 0.108. So I'm going to get 1 and 2. So I don't need to worry about multiplying till whole, because I already have whole numbers for my empirical formula. So my empirical formula, I'm going to have 1 nitrogen and I'm going to have 2 oxygens. Okay, so that is my empirical formula. Now I just need to find the molar mass of this so that I can plug it into this equation. We already have the molar mass. The larger number is 92, so we just need to find the molar mass of this to plug that in for the empirical mass to determine our multiplier. So the molar mass of NO2, I would take nitrogen plus 2 times the mass of oxygen and get 46.01 is my molar mass. So if I take my molar mass, which is my larger number, 92, given in the problem, divided by the molar mass of the empirical formula, so 46.01, I get a multiplier of 2, so this is our multiplier. Okay, and so we're just going to take the empirical formula and multiply each of the subscripts by 2. So my molecular formula will be N2O4. Lastly, we can also find the percent purity, which is just the percentage of a pure substance in an impure sample. So the equation for percent purity is the mass of the pure compound in the sample divided by the total mass of the impure sample. Okay, and since it is percentage, we are going to times that by 100. So the mass of the pure compounds, whatever the pure substance that we're trying to determine the purity of, like in the example we have here, it's going to be copper, and then the total mass of the sample, not just of the pure substance. So for example, a 150 gram sample of copper ore contains 87.3 grams of pure copper. We're going to calculate the percentage of purity. So for our pure copper, okay, this is our mass of the pure compound, so that goes on top, so 87.3 divided by the total mass of the sample, which was 150, and then again, it is a percentage, so we're going to times by 100, so this is 58.2% pure. Okay, for this one, I did include sig figs here, so I had 3 sig figs in my answer, because if we look back, this has 4 sig figs, this has 3 sig figs, and we always go based off of whichever one has the least number of sig figs. So this one has 3, so my answer has 3.